Well, good afternoon, class. This is our video lecture for Tuesday, the 19th of September. This is Dr. Harn, and I want to start off with a reminder that today also corresponds to the due date for the second homework today, due to 19th September. And slide under door at Scott Lab E540, which is my office. So don't forget, do that before, say, midnight tonight, and I'll be able to grade that and get it back to you as quickly as possible. So we'll start off this video lecture with a quick review about time harmonic acoustic plane waves, and extend these concepts to a few other important aspects about plane waves. But recall that plane waves mean that the acoustic variables are constant in given cross-section. So, for instance, So, for instance, we may have plane waves in a lot of HVAC applications, heating, ventilation, and air conditioning applications, where noise is created by fans and ducts, or tubes or pipes, whatever you'd like to call them, and then that noise is propagated along that duct, and typically what we have in these ducts are these little vents, and this is the vent that's in the room in which you sit, and waves can propagate a long way, very long way. In fact, the cross-section may even change, so it may step down into a smaller area and then keep going. But so long as we're dealing with the case where in any given cross-section the acoustic variables of pressure, particle velocity, and density are constant, then we have the case of acoustic plane waves. So let's recall some of these characteristics of plane waves. And since they're similar to the longitudinal deformations of the rod, we can write out this expression just in a similar way. A complex amplitude, e to the j omega t minus kx, k is that wave number, plus complex amplitude b, e to the j omega t plus kx. And indeed, this satisfies that one-dimensional acoustic wave equation. You can check that out yourself. But drawing from this form of expression for acoustic pressure, we can find the particle velocity using Euler's equation. And while the general form of Euler's equation is minus del P del X is equal to rho naught del U del T, for time harmonic waves, we have that it's minus del complex P del X is equal to J K rho naught c times the complex particle velocity. And we found, by substituting in this forward and backward x propagating waves components, we are able, in fact, to express that particle velocity as forward and backward components using similar forward and backward signs via the respective pressure components divided by rho naught c. And so, using an expression of the complex specific acoustic impedance as the pressure on the particle velocity, writing that out, the complex specific acoustic impedance we found that based on the direction of wave travel, this leads to the result that the specific acoustic impedance is either plus or minus rho naught c, which depends on the direction of that plane wave travel. So this is an energetic measure. Being purely real, this for plane waves corresponds strictly to energy transfer. Because the impedance is purely real. And impedance is not the only important energetic measure in acoustics. There's another that we'll introduce right now. So another energy measure in acoustics, used in many practices, especially noise control, called acoustic intensity. And like other measures that are sometimes dealing with harmonic waves and sometimes not, we start off by introducing instantaneous acoustic intensity. And in general, this is a vector, so we'll put a overbar on it. So the instantaneous acoustic intensity is determined as the product of that time harmonic pressure, or rather the acoustic pressure and the particle velocity, both of which are generally functions of space and time. Because this is more than just a time-dependent P and time-dependent U, I'll leave out their spatial dependencies because it's dependent on the coordinate system. But the units here are watts per meter squared, and so seeing watts suggests something about work and power and energy. And putting this into words, it's the rate at which work is done by one fluid element on an adjacent or neighboring fluid element. So the instantaneous acoustic intensity is the rate at which work is done by one fluid element on a neighboring fluid element. But because we often deal with these time harmonic acoustic waves. We don't typically deal, or we don't typically have interest in these instantaneous quantities of intensity, so we very often instead look at time average acoustic intensity. Which is still likewise a vector, but no longer adopts the time dependence, because we will get rid of that. But in the future, we'll use intensity throughout this course. Because we rarely, if ever, need the instantaneous quantity, whenever we refer to intensity or acoustic intensity in the future, we imply time average acoustic intensity. And of course, if we're starting with our intensity as a product of the particle velocity and acoustic pressure, just take the time average of those two quantities, and that gives you the acoustic intensity. So in other words, 1 on time, the integral on time of the acoustic pressure and the particle velocity. Now, note, however, there are no complex quantities here. So we specifically mean that if it is a complex expression, we have 1 on time, 0 to t, the real part of the acoustic pressure multiplied by the real part of the particle velocity vector, integrated on time. Now, for plane waves, this gets simpler. Because the particle velocity is no longer a vector. It's just a scalar in the one direction of interest. So that means this time average can be simplified a little bit. So for instance, we can drop the hat on the time average acoustic intensity because it's no longer a vector. Now it truly is just a function of position wherever the acoustic pressure or particle velocity are. So by substitution, you find that we have the mean square of the acoustic pressure divided by the specific acoustic impedance, rho naught c. Or doing a different substitution, we'd find that it's the product of the specific acoustic impedance and the mean square of the particle velocity. So this is alternatively simplified, thinking about these mean square or RMS quantities as being the product of the RMS of acoustic pressure times the RMS of particle velocity, which by substitution, using similar routines again, leads to PRMS squared divided by the specific acoustic impedance, rho naught c, or introducing an amplitude of acoustic pressure squared divided by 2 rho naught c, and writing this out, that P is the amplitude of the pressure. Say it's a complex exponential notation. Now in general, in the 3D case, time harmonic case, the acoustic intensity, in other words, the time harmonic acoustic intensity, or in other words, the time average acoustic intensity, is still a vector in general 3D, but it can be computed as 1/2 the real part of the acoustic pressure complex times the complex conjugate of the particle velocity. And you can demonstrate this by substitution yourself to find that, in fact, the product of the complex acoustic pressure and the complex conjugate of the particle velocity does indeed lead to the vector component of the acoustic intensity. So acoustic intensity for plane waves, so for plane acoustic waves, the acoustic intensity is independent of that spatial location x. So in other words, energy propagates without attenuation. And specifically, without attenuation over a given area. So because it's watts per meter squared. We're calling those units watts per meter squared. But we have innumerable or many experiences day to day where we have it in our head that waves do in fact reduce in their energy as they propagate. But this is because we're surrounded day to day, unless we work in ducts all the time, we're surrounded by spherical waves. So intensity in fact takes on a much more interesting result in the study of spherical waves. So let's look into spherical waves, but specifically we'll dive right in to harmonic spherical waves. And we'll first introduce these today during this video lecture, and we'll cover them in greater detail on Thursday, the 21st of September. So, harmonic spherical waves, returning to that 3D acoustic wave equation, where we had the Laplacian operating on the acoustic pressure is equal to 1 on c squared, the time the acceleration of the acoustic pressure, using the spherical coordinate Laplacian, and assuming that elevation and azimuthal dependence, so the elevation angle theta and the azimuthal angle phi, and assuming that elevation and azimuthal angles do not influence wave propagation. So in other words, considering waves propagating in different angle combinations doesn't actually change the propagation characteristics, which is absolutely the most common thing that we are exposed to day to day. This leads ultimately to an acoustic wave equation written as del squared, the quantity r times p, divided by del r squared is equal to 1 on c squared del squared, the quantity rp, del t squared, where that r is the radial distance from the coordinate origin in the coordinate system origin. So imagine you have a speaker at the location where R is 0, and the speaker is radiating sound away. So we have experienced that at least reasonably far away from acoustic sources, there's no azimuthal and elevation angle dependence. Now, what's interesting is that this equation for spherical waves has an analogy to the wave equation for plane waves. Which we can write out again here. So we see that everywhere there was just a P in the acoustic wave equation for plane waves, if we substituted an RP, so P to RP, we would basically have the same thing. So this analogy leads us to guess that a general solution to that spherical AWE, which I will bring back up to our front right there, is of form R times P is equal to some function of the argument CT minus R now, plus some function F2 CT plus R. Now let's examine this a little bit further, because we're ultimately interested in acoustic pressure. So, for acoustic pressure, that means the general solution could be P is 1 on R times that function 1 with argument CT minus R plus 1 on R times that function 2 with the argument CT plus R. Which, of course, given that our origin starts at R is 0, this is valid only for R is greater than 0. So what do we have here? Well, this function 1 characterizes outward propagating waves. So outgoing spherical waves. And these are what we're familiar with. We speak, and the waves propagate outward, but they're reducing in amplitude in proportionally with 1 on R. As we get further away by a factor R, the amplitude of that acoustic pressure wave will reduce in amplitude by about 1 on R. Now F2 is interesting. It characterizes incoming spherical waves. we don't have many instances of this in the real world, because these increase in amplitude as they're converging to some origin. So they increase in amplitude, ultimately to increase, astronomically to some extreme value at the origin. So these are convergent waves, which are non-physical. They mathematically exist, and some very good experimentalists could maybe reconstruct something like this, but they do not occur in practice. So moving forward, we omit or we neglect the waves associated with this F2, and instead only consider waves of the form one on R of the function Ct minus R. And if we do that substitution and do similar operations as we have done with harmonic acoustic plane waves, we find that the complex spherical acoustic waves are of the form the complex amplitude divided by R multiplied by e to the j omega t minus k r, x being simply replaced with R. So this is similar but quite different than harmonic plane waves. The amplitude is the overall amplitude, so this is the overall complex amplitude. So this together has units of pascals, which means the A here has units pascals meters in order to make the units work out on pressure. Whereas here what we have is that propagating component repeats every 2 pi, right, due to Euler's identity. But uniquely here we have that 1 on R relationship, which is what we're familiar with. So then I'm writing so a lot. So then for the time harmonic Euler's equation, we have that minus del P del R is equal to rho naught del complex U del T is equal to J K rho naught C. That as much does not change. But what U becomes after doing the substitution of this for P rather than the plane wave expression, what the particle velocity will be found to be is very different. And this is what we will cover when we meet in class on Thursday, the 21st of September. So with that, if I can get this back up on the screen, with that, we will wrap up this video lecture, and I look forward to seeing you soon in class. See you soon.